Hello, everyone. Thanks for joining this extra session. Hopefully, it will be a short one, quick one. So I'll get started right away. We were talking about the SPC code, and specifically, we drew this diagram, which we call bipartite diagram. So all that it does is to show us that if I take this 4 encoded bits of an SPC rate 3/4 code, right? This is rate 3/4. R is equal to 3/4. And if I add them up, I am guaranteed to get a 0. Why? Because that is how this SPC is defined. We add this parity bit in a manner so that there is always even number of ones in this 4 bits, C1 to C4. And so no wonder when we add C1 to C4, we are guaranteed to get S1, which is 0. And that is what is indicated by this bipartite diagram, where these connections mean that at S1, these 4 nodes are getting added up. So now what I would like to ask you is to draw the bipartite diagram for rate 1/5 repetition code. Right. So for rate 1/5 repetition code, maybe let me start by saying that there is only one information bit. So instead of drawing 3 information bits, I will have only one information bit. Right. For SPC, I had M0, M1, M2. Here, it's not like that. There is only one information bits. How many parity bits should I draw for rate 1/5?
4.
4.
Parity.
Correct. So let us draw this 4 parity bits, P0, P1, P2, and P3. And then this becomes the coded bits, right? So this becomes C0, this becomes C1. It's very much like what we drew earlier. This is C2, this is C3, and this is C4. Okay. So now the question for you is to tell me how to draw those S bits for this bipartite graph of the repetition code. Let's call those S bits supervisory bit, because they kind of supervise it. Okay, all the bits that are connected to me, they have to sum up to 0. Right? I mean, maybe it's a name that I have come up with myself. I don't think that is very widely used in the literature, in the textbook, etc. But that is how I would like to. I like to think of those S bits. All the bits that are connected to the S bit have to sum up to 0. Okay, so who can tell me how to draw the remaining part of the diagram? First of all, how many S bits should I draw?
4.
Yeah.
4.
Yeah, you're right. So it should be 4, because we are adding 4 extra bits. So there should be 4 supervisory bits. I will call them S0, S1, S2, and S3. So these are the 4 supervisory bits. So the only thing that remains is to draw the edges or the connections of this bipartite graph. So what should be the connection of S0?
Each with one parity. M0 with
Exactly. So push is correct. So S0 checks that C1 and C0 add up to 0, meaning they are the same. Then S2 checks that C0 and C2 are the same, meaning they add up to 0 modulo 2. Then S2 checks that C0 and C3 are the same, and S3 checks that C0 and C4 are the same. This is how we can draw the bipartite tag diagram for rate 1/5 repetition code. Now, you can just look at this diagram and draw the parity check to write the parity check matrix. Okay, the parity check matrix is nothing but each row of parity check matrix defines each of the supervisory nodes. So S0 is going to be 1, 1, and the other three connections are 0. So the corresponding row will have just 1, 1, 0, 0, 0. S1 defines the second row of parity check matrix. So the corresponding values will be 1, and there is no connection here, so 0, then 1, 0, 0, and so on. Okay, so it's very easy to draw this bipartite diagram if you can write H matrix. Or if you have already written H matrix, if you already drawn the bipartite diagram, then from that you can easily write the H matrix. And yeah, I want to emphasize that you want to think of this square nodes, which also, by the way, remember, they can take values of zeros and ones. Each of these square nodes, supervisory nodes, can take values of zeros and ones. When will it take? All of them will take values of 0 when the received bits are exactly the valid code words. If it is valid code word, you are guaranteed that each of S bits will be 0. But when you receive something in error, some bit is in error, then one or two or multiple of these S bits will become 1. So you want to think of S bits as kind of supervisory bit. Whenever a particular check is met, they are happy and they are 0. When a particular check is not met, they become unhappy and basically they say that there is a problem here, I am 1. Okay, so with that aside, now let us jump into the next coding scheme, which is quite an interesting scheme. You know, it's probably not going to be terribly difficult for you to appreciate. And it's called a product coding scheme. So we'll first take a look at what is known as square product code or square parity check codes. And the reason why it is called square is because the number of information bit is always a square number, right? So the number of information bits is either 4 or 9, 16, etc. And also the number of encoded bits is also square. It is essentially a square root of k plus 1 whole square. So why is that? Well, so the way we do the encoding is by having multiple SPCs. Remember, I had mentioned earlier that pretty much all of the other coding schemes that we will be looking at, other than SPC, can be thought of as multiple SPCs combined in a clever way. I mean, that is what we saw here with right, with the repetition. This repetition code is nothing but 4 SPCs put together. where all these four SPCs are feeding off of there's just the same message bit. But it doesn't have to be just the same message bit. That is where variety of the coding schemes come into play. And this product coding is one such scheme. So the whole idea is that, we'll consider the case of k equal to 4, and when k is 4, n is going to be 9. If you plug k equal to 4 in this formula, you will see that n will be 9. So we are going to put, we are going to take an example of rate 4/9 product code. And with the bullet points, we are going to just see them by diagrammatic way. So what we do here for the product code is that we take these 4 information bits. Okay, for some reason, instead of calling them M0 to M3, here I'll call them M1 to M4. So notation, little bit of notation inconsistency on my part, but please bear with me. So yeah, so we have 4 information bits and we put them in a square manner. You see, that is why it's called a square parity check code. M1 goes here, M2 goes here, M3, M4. So it became a square. Now what we do is we put an SPC code on each row and each column of this square. So P1 is the SPC of M1 and M2. It's basically XOR of M1 and M2. P2 is the XOR of M3 and M4. P3 is the XOR of the column, so M1 and M3. Right? P3 is M1 plus M3. P4 is the XOR of M2 and M4. And then finally, just to make the outer square also completed, we put P5, which is actually parity on the parity. We have already calculated the parities for P1 and P2. And we have calculated parities P3 and P4. And then P5 is going to be XOR of P1 and P2. Or it will be the same as XOR of P3 and P4. Okay, so now what I would like you to do on your own, whenever you have time, is to determine the G matrix and the H matrix. And also the bipartite graph. Of this square product code or square parity check code. Okay, so please do it on your own. But now what I'm going to do is, let us see quite an interesting scheme that we can use to decode this product code. You see, we have studied how to decode a repetition code. We also saw how to decode an SPC code. Decoding of SPC code is super simple. We just sum up all the n bits, and if the sum is 0, we say most likely no errors have happened, or it could be that 2, 4, even number of errors happen. And if the summation is 1, then we say that yes, some bit is in error. Only thing I can tell you is that errors have happened. I can't do anything about it. TD is 1, TC is 0. So that was the decoding for SPC. For this one here, decoding is not that trivial, but it's pretty simple and it's pretty interesting. So that is what we will look at now. So to make the discussion clearer, I have taken a very specific example. Okay, so let us say that M1 is 1, M2 is 0, M3 is 1, and M4 is 1. This is a very specific example I'm taking. And then I just calculated the parities, right? So P1 has to be 1, right? Because then only this SPC will have even parity. P2 has to be 0 because the second SPC already had even parity. So if I added 1 here, then it will have odd parity, which doesn't work. And so likewise, I have calculated all of these 5 parity bits in this manner. Now, for the sake of simplicity, I'm going to consider the binary eraser channel, okay? Not the BSC. Remember the binary eraser channel, how it looks like? The transmitter still sends zeros and ones, and hopefully majority of the times with a probability of 1 minus p, the receiver will get 0 if the transmitter has sent 0. The receiver will get 1 if the transmitter has sent 1. So whenever the receiver gets 0 and 1, it has no doubt about what the transmitter sent. The problem is that sometimes the bits get erased. The receiver doesn't get anything. And that happens with a probability of p. So we are considering this type of eraser channel. When a particular transmitted bit gets erased, obviously the receiver doesn't know whether x is 0 or 1. So for this type of channel, how to do the decoding? And again, for this particular example, I'm going to assume that BC is pretty bad if it has erased 5 bits out of the 9 bits that were transmitted. Right? So all of these 5 bits got erased. The receiver didn't get anything. But it got the 3rd bit, 4th bit, 5th got erased, it got 6th bit, and then 7th bit. And then the remaining 2 bits didn't come out. So how to then do the decoding? So the way the receiver will do the decoding is it will fill up the same square. Except wherever there are erasers, it will put a question mark, like what I have shown here. Okay. Now, the receiver will start doing SPC decoding. But it will do SPC decoding first on a row by row basis. And then when it is done on row by row, it will go to column by column. And then after it is done column by column, it may again start doing row by row. And so that is why this is called an iterative scheme. The decoder kind of iterates over rows and columns. Okay, so now I'm going to ask you, so this is the starting point. This is where the receiver is when it, oh gosh. Good. I flipped one slide too fast. Okay. So this is where the receiver is, and it started doing row by row. So when it looked at the first row, 2 out of 3 bits got erased. And so in this case, it can't do SPC decoding. For the second row, you might have already seen the answer. It can do the SPC decoding. What should it put here for this question mark, for this eraser bit?
1.
It should put 1 because that is how the second SPC is satisfied. So that is what it will do. Can it do anything for the third row?
No, sir.
Okay, so then row by row is done. Now let us look at column by column. When it goes to the first column, does it have any hope?
Yes, sir.
Yes.
Yes, sir.
Yes, it will
One,
be
only one.
One.
So what will it do for the first row, first column?
One.
One. Place one there.
It will put 1. What about the second column?
0.
no.
No,
No.
nothing.
First
Not.
No hope.
can't
No.
say anything.
Yeah. Second column, how can it put 0? Where will it put 0?
Second column, first row.
Second column, first row, it will put 0?
Yeah, sir.
Yes.
No, sir.
No. When it is doing column by column, it is
Would
only
have to
looking at the
check.
column.
Yes.
Cannot put anything there.
See, when it looks at the second column, there are 2 erasers. So it
Oh,
can't do
okay.
this
Sorry, sir.
decode.
Okay.
So it will skip the second column. What about the third column?
One.
It will put 1.
One.
One at the last.
So for this one, it will put 1.
One.
Okay. So after iteration 1, it actually unerased 2 bits. Or no, actually it unerased 3 bits. In the first part of iteration 1, it unerased this bit, and in the second part, it unerased these 2 bits. So now it will go to the second iteration. Now it will do row by row again. So when it does the first row, does it have any chance?
Zero.
Yes, sir.
Yes. Zero.
Zero.
0. Second row is already done, so it doesn't have to work with the second row. Third row,
One.
One.
yeah. And so actually in the second iteration, by the time it finished row by row, it is already done. It doesn't even have to go to the second part of column by column iteration. You will see that all of the unerased bits all of the erased bits have been successfully unerased. This exactly was the transmitted code word. Right, so this part here, this was the transmitted code word. Although 5 out of 9 bits got erased by this iterative example, at the end, the receiver was able to recover exactly the same transmitted code word. So this is the way that the decoding works for the product, at least for the BEC. Okay, now I just wanted to mention that what we looked at was a square arrangement, but it doesn't have to be square. It could be rectangular also. So instead of having the same number of rows and columns, you can put bits in number of rows which is different from number of columns. But the idea remains the same. You put a parity bit on each row and each column. So I'm going to put a PDF, which is lecture number 6 of some Massachusetts Institute of Technology channel coding course. And look at this figure 6.3, and it will give you an idea of what the rectangular parity check code looks like. Now the numbers doesn't have to be square anymore. So 8 and 14, they are obviously not squares. But other than that, everything else is the same. The decoding also works in the same manner. Okay, and then the last scheme that I wanted to show to cover is called the Hamming code. Okay, this Hamming code is pretty one of the very initial designs done by engineer called Richard Hemming, and he did a lot of nice work in the coding theory, and so that is where this Hemming weight, Hemming distances, minimum Hemming distance, all of those terminologies came from him. He came up with this particular coding scheme, which people find it very nice and beautiful. And we will see why it is like that. So what he said is that I will take 4 information bits at a time. And remember, everything is just a combination of SPCs. So he said that I'm going to use 3 SPCs. So there will be 3 supervisory nodes. And these are the formulas by which Hemming code calculates the parity bits. So the first parity bit is the XOR of M1, M2, and M4. Second is the XOR of M1, M3, and M4. The third is the XOR of M2, M3, and M4. So again, this time I have given you the bipartite graph of the Hemming code, right? So this is the bipartite graph. So when you do the this for the product code, the rate 4/9 product code, after you are done with that, please also determine the G and the H matrix for the Hemming code. And you will see that columns of H have some interesting pattern. So if you can see what that pattern is, let me know. And the other thing that you may be able to observe is that for all of these coding schemes, if you have H, you can get G, or if you know G, then you can very simply write H. So see if you can find out that relationship between H and G. Okay, now one thing that I want to mention is that this RPC code that you will study in this MIT lecture, its rate is also 4/7, and this Hemming code rate is also 4/7. It takes 4 bits and generates 7 bits out, and it adds 3 parity bits. And although we haven't done that calculation yet, we will show this maybe in the subsequent lecture, that minimum Hemming distance for this code is identical. It is 3 bits. But still, Hemming codes are slightly better than the RPC codes. Even though their DH min is the same and the rate are the same, Hemming codes actually perform slightly better. And the reason is that you will see that here, each of the supervisory nodes has the same number of connections, right? They all have 4 connections. So basically, each of these supervisory nodes kind of take up the task of recovering from error in an equal manner. Whereas for the RPC code, rectangular parity check code, some supervisors have more connections, more edges. Some other supervisors have less connections. And that kind of little bit disturbs the decoding. Okay, let us see. I think all of this we are not going to do now. So we will end here. And then some properties of linear block code is what we will take up when we meet next time. So I'll be posting the slides up to slide number 72. on the shared folder, the Google Classroom, and